In this video, I want to talk about cyclic groups. This is something I had defined in a previous video, but I want to look at them a little more closely this time. To start, let's remind ourselves what a cyclic group is. If G is a group and every element of G is a power of some group element A, then G is cyclic. In other words, G is the set of all a to the n, where n is an integer. So we're looking at all of the powers of some given element A. We write that as G equal to A inside of angled brackets, and we call that element A the generator. So every element of my group G is some power of this element A. Let's suppose we have some cyclic group G generated by A, and we know the order of A is n. Then we can say that G is a cyclic group of order n. We showed in a previous video that if we have that the order of A is n, then we have a set of elements that includes all of the powers of A and they're all distinct. So we would have a cyclic group of order n. We would have exactly n elements in that group. As an example, the integers under addition form a cyclic group. So in order to form a cyclic group, I need to know the generator. For the integers under addition, we would have 1. The fact that they're under addition means instead of powers, I need to look at multiples. So we have 1 plus 1 is 2, 1 plus 1 plus 1 is 3, and we can keep going in this manner. We can also subtract. That would be the equivalent of the inverses. 1 minus 1 is 0. 1 minus 1 minus 1 is negative 1, and we can get the rest of the integers this way. So this would be a cyclic group under addition with a generator of 1. Let's consider a cyclic group of order n generated by A. This means I know that this group consists of the elements e, a squared, a cubed, etc., all the way up to a to the n minus 1. We also know that Zn consists of the elements 0, 1, 2, 3, etc., up to n minus 1. We can show that these two groups are isomorphic. In order to do that, we're going to build this function f going from Zn onto our group generated by A, defined by f of I equal to a to the I. We can see pretty easily that this is bijective. We have things in the corresponding positions in these two lists. So what we really need to show is that f of I plus j is equal to f of I, f of j. Well, f of I plus j, that would mean a to the I plus j power. Properties of exponents gives me that this is a to the I times a to the j. A to the I is fi, and a to the j is fj. So this is an isomorphism. So if we know that A has order n, then the group generated by A is isomorphic to Zn. In addition, if the order of A is infinite, then we have that A is isomorphic to Z using this exact same function. Let's do a quick summary of what we just showed. The first thing, for every positive integer n, every cyclic group of order n is isomorphic to Zn using the isomorphism we just had. This means any two cyclic groups of order n are isomorphic to each other. So a cyclic group is completely identified by its order. Once we know the order of the cyclic group, we can say everything we need to about it by knowing it's isomorphic to Zn, as well as every other cyclic group of that order. And there's nothing unique about finite order. Every cyclic group of order infinity is isomorphic to Z, which then tells us as well that any two cyclic groups of order infinity are isomorphic to each other.